Hello and welcome. In this video, we're going to talk about energy and power. Energy is the ability to do work. We have energy ourselves, right? We can consume food and that's going to provide us with energy so that we can do more work. Well, we're going to do the same thing with our power systems here, except for we're going to call work joules and we're going to key it with a W. We're going to say W equals, that's going to be work is equal to, and we're expecting a joule output there. Sometimes we have another factor that we can use for that. If we know the rate that the energy is used in, we'll call that power. Power is equal to the work that we did over the time it took us to do it. Right? So sometimes we can even call work kilowatt hours. Right? We see that quite often. Kilowatt hours, that's the multiply of our power and our time. Right? And that is the same thing as if we were to rearrange this equation here, multiply t to both sides, and we get power. Work is equal to power times time. And that's what we're talking about with the kilowatt hours. So that's going to be a consumption of energy over time. And that's the usage of that energy. Just keep in mind that if you're working with joules in terms of work, that you need to be working in seconds in terms of time. Right? You need to pair those together. If you have joules, work with seconds. Okay, so I'm going to give you an example of how we're going to use these, and it kind of flips back and forth. We do have a sun up here, and that is going to be given energy to all of these solar panels. These solar panels are going to produce a current flow, right, electron flow through our pump down here. It's going to feed the pump potential, and that potential is going to allow that pump to turn, and it's going to take the zero potential energy down here, and it's going to feed it up to this upper level here, and we're going to store the gravitational energy that we get at the top here. Until the nighttime. And then at night, we're going to allow that gravitational potential at the top to flow back down through what we call a turbine at the same location as that pump. One direction it's a pump, the other section it's a turbine. It generates an energy that we can then consume at night. So let's hit play on this and we'll watch this as it flows. So solar panels pull in the energy for that kinetic transfer up here, and as it's completely full, it becomes nighttime, and that pump allows it to flow backwards through a turbine right here, and that lower pool fills back up, right? So we pull water out of the bottom and back down, and we just rotate that back and forth, and that's allowing us to consume energy at night using a different potential other than the sun. Let's go down one here. This is how we're going to characterize our power value. We see over here on this side that we have a potential, a positive and a negative, and we call that V. So voltage is going to be our potential for our electric circuits. And then we see this I up here, and that's going to be the flow, these plus signs as they travel through here. That's the flow of electrons that we talked about before, the valence shell, you know. And we have a high potential at top. That's why it is yellow at the top here. It has a high potential. And as it goes through this resistive component, it's going to lose potential, right? And that resistive component is going to keep the power, right? And that's just the same as when we drop the rock onto the surface, right? As soon as that rock hits the ground, it transfers its power. As soon as our current flow hits this resistance, it's going to consume its power, right? And then it's going to be moving back down here with less potential. It doesn't have any more potential because it's at the negative terminal. It's at ground, right? And that's our lowest ionization right there. So that means that we can characterize power in terms of work and time, like we just did, or we can also characterize power in terms of the voltage potential that we have and the current flow of electrons that we have. And we're going to call those voltage in volts and current in amperes. So we're going to give current an A at the end to represent that current flow. This is our power triangle up here. So if we wanted to ever remember this equation here, we can use our power triangle. You can just put P on top, I and V on bottom, in any order on bottom there. And then from there, you can circle the equations that you want. So if you have the need for power and you have voltage and current, you can say power is equal to I times V. That's the power equation. We can also say, what if we know power and voltage and we want current? Well, we can say I is equal to power over voltage, right? They're above each other there. We can do the same thing for voltage. If we want to know the voltage potential in the circuit, we can say that the voltage is equal to the power over the current, power divided by current. Right? So we can know any one of these or any two of these values and get the other one out. And that's the nice part about this power triangle here. Okay, let us know if you have any questions.